All right, hello AP students and welcome to your post lecture and the end of new material for Unit 2. We previously talked about Lewis structures, the 2D illustration for molecular bonding. Then we moved into molecular geometry, the 3D. Then we moved into valence, valent hybridization and valence bond theory, which integrates the quantum mechanical model with the concept of how do we get these molecular geometries. And now I am going to quickly introduce a kind of like a separate category of how to characterize bonds as sigma and pi. And of course, I'm about to compete with the leaf blower. So sigma bonds, represented by the Greek symbol sigma, are when orbitals overlap to form a bond that lies in the same plane as the nucleus. So an SS overlap or an SP in the same XY or the same YX coordinate would be considered sigma. Or a PP in the same PP hybridization overlap would also be considered a sigma, as long as it's in the same plane. Okay, and all bonds, by the way, contain at least one sigma. So a sigma bond is in every single, double, and triple bond contains a sigma bond. All right. Again, this categorization of sigma versus pi is creating another kind of layer of identification of bonding and merging, further excavating the concept of how the quantum mechanical 3D orbital suborbital model makes sense with what we know to be true in terms of the 3D spatial arrangement. All right. So pi bonds, on the other hand, are when orbitals overlap to form a bond in regions that lie side to side. Okay. Or parallel. So this would be a pi bond, and these would all be sigma. So a pi bond occurs when generally p orbitals overlap. Okay. Or you could have d orbitals, but again, you're not really going to be asked to know the d level of hybridization or valence bond theory. Okay. They are always present in double and triple bonds. And they are generally weaker than sigma bonds. So what you're seeing is that for a single bond, okay, such as C2H6 structure, such as the bonds in C2H6, we have what we'd call is one sigma bond, such as to make up a single bond. For a double bond, we see it's one sigma plus one pi bond. We see one in the same plane overlap of the orbitals plus one parallel orbital overlap to create the double bond. Okay, and then for a triple, we see one sigma plus two pi. All right. I recognize completely that this seems like, how does this all merge? And if you sit down with it, you might need to watch an Organic Chem Tutor video to really parse this out with you. But the idea is that, again, you are merging the concept of how do we take the quantum mechanical 3D model of orbitals, okay, with valence bond theory that continues to excavate that and pair it with the known 3D structure through molecular geometry and how we get these molecular shapes. And sigma and pi bonding is just one other way that we categorize everything to make it all come together. So go ahead and try these practice problems. Consider acetonitrile molecule, predict the bond angles around each carbon atom, describe the hybridization, and determine the number of pi and sigma. All right, guys, so hopefully this is what you got for each of the following A, B, and C. Now notice acetonitrile has two carbon atoms, so you have to address each carbon as a relative central atom and look at each carbon as, well, their respective central, and then determine the geometry based off of that carbon's position. I hope at this point you're pretty familiar with hybridization. And then the newest part is, of course, the sigma versus pi. In the entire molecule, I have 4 singles plus 1 triple, giving me 5 sigma. And then that triple consists of 2 pi. So good job, you guys. This is kind of the end of it all. And good luck studying for your unit 2/3 test. Bye.